Welcome to the Explainer. Today, we're taking a super focused visual journey to totally unlock the secrets of quadratic functions. Over the next 10 minutes or so, we're going to break down exactly what quadratics actually are, translate those kind of clunky mathematical formulas into crystal clear visual shapes, and run through some real examples that'll make the whole thing just click. So if you've ever stared at a complex math equation and felt a little lost, well, you're in exactly the right place. It's the ultimate question, right? What exactly is a quadratic function? I know, just hearing the word quadratic can instantly trigger a bit of math anxiety for a lot of us. It sounds abstract, complicated, maybe even a little intimidating. But today, we're completely shifting that mindset. We're going to flip that anxiety into pure curiosity by looking at exactly what's going on behind the scenes of these equations. Okay, so here's our quick roadmap for today's explainer. We'll start with the anatomy of a quadratic, meet the parabola, go over some graphing and shifting examples, and finally, look at finding the solutions. All right, let's just dive right in. Kicking things off with section 1, the anatomy of a quadratic. Let's break this equation down. So every single quadratic equation out there can be wrangled into what we call standard form. That's ax squared plus bx plus c equals 0. Now, don't let the alphabet soup scare you off. The letters A, B, and C, they're simply constants, just stand-ins for regular numbers or even decimals. But there's one absolute golden rule here. A can literally never equal 0, because if it does, poof, the whole quadratic nature just completely vanishes. Let's actually deconstruct that equation term by term so it's a bit more digestible. That first piece, the ax squared, that is the quadratic term because it's raised to the second degree. The second piece, bx, is the linear term, carrying a degree of 1. And that lonely little c sitting at the end, that's our constant term, possessing a degree of 0. And you know, this brilliantly illustrates exactly how each piece of the equation gets its name. It's all dictated by the degree, or the power, of that specific term. Moving right along to section 2, let's meet the parabola and put some visual shapes to the math. Whenever you map a quadratic function onto a coordinate plane, it always creates a very specific, undeniable shape, the parabola. This is that signature, sweeping U-shaped graph created by plotting our equation. Seriously, every single quadratic equation in existence forms this exact U shape. But wait, how do we know which way that U is going to face? Well, it all comes down to what we call the A factor. Remember that very first constant A from our standard form? Its sign completely dictates the direction of the shape. If A is positive, meaning it's greater than or equal to 1, the parabola opens up, kind of like a bowl holding water, making its bottommost tip the minimum point. But if A is negative, the whole thing flips and opens down, like an umbrella, and that makes its peak the maximum point. Let's quickly map out the key landmarks of this parabola. First up is the vertex. That's the turning point we just talked about, either the absolute maximum or the absolute minimum. Passing right through that vertex is the axis of symmetry. Think of it as an imaginary vertical line that just perfectly splits the parabola into two identical mirror image halves. Then we have our intercepts. There's the y-intercept, where the curve crosses the vertical axis, and then, absolutely crucial, the zeros or roots. These are the exact points where the curve crosses the horizontal x-axis, and they are literally the mathematical solutions to the equation we're looking for. All right, section 3. Let's look at some graphing and shifting examples to see how we actually move this parabola around. We're going to start with our anchor. This is the most basic, foundational quadratic graph in existence. Y equals x squared. Because A is a positive 1 here, it opens upward. And its minimum point, its vertex, is sitting perfectly anchored right at the origin of the graph. Good old 0, 0. Now watch what happens when we make just a tiny little tweak. By simply subtracting 2 at the end of the equation to make it y equals x squared minus 2, we literally drop the entire graph straight down. The U shape itself is completely identical, but the minimum point has plunged 2 units right below the origin. Let's see how this builds. Now we have y equals, inside parentheses, x minus 2 squared minus 2. By grouping that minus 2 inside the parentheses with the x, we've actually forced the graph to shift to the right. And then combined with that minus 2 on the outside, our parabola has essentially traveled 2 units down and 2 units to the right from our original starting point. Keeping up the pace here, look at y equals, in parentheses, x plus 5 squared minus 1. Now, you might logically think a plus 5 inside those parentheses would move things to the right, right? Actually, no. It slides the entire graph 5 units to the left. It's a fantastic little math plot twist. And then that -1 on the very end, it simply drops the whole thing down a single unit.
Finally, take a look at this one. Y equals negative, in parentheses, x minus 5 squared plus 3. As our source material wisely advises, don't get frightened by this graph. All that's happening here is that the negative sign sitting at the very front has simply flipped our U-shape upside down. So it's now facing downward, shifted 5 units right, and 3 units up. It definitely looks complex at first glance, but it's really just following those exact same basic rules we just learned.
Beyond just shifting the equation around, you can really see the structure of a quadratic just by plugging numbers into a simple table. Look at these values. Our vertex is situated right where x is 3 and the function output is -4. But check out the outputs right above and below that vertex. They are both 0. The f of x values repeat perfectly, just like a mirror on either side of the vertex. And this perfectly numerical symmetry is exactly why the graph creates that flawlessly symmetrical U-shape in the first place.
Okay, moving into section 4, finding the solutions. Let's figure out how to systematically calculate those zeros.
Thankfully, algebra doesn't leave us hanging. It gives us a whole toolkit for finding these solutions. We can use factoring, a neat technique called completing the square, the famous quadratic formula, or we can simply just graph it out. But the absolute crucial point to remember is that no matter which of these methods you choose to run with, they are all ultimately trying to do the exact same thing. They're trying to find the precise coordinates where that sweeping curve perfectly hits the horizontal x-axis. Now, before we wrap things up today, let's talk about the so what. Why even go through the effort of mastering parabolas and 0 points? Well, our sources highlight something absolutely critical. Mastering quadratics right now is essential because they are the hidden key to much harder math later on. When you start tackling complex systems of nonlinear equations, substitution methods will almost always dump a quadratic equation right squarely in your lap. So if you know how to handle them now, you are going to be pretty much unstoppable later. Which leaves us with this final thought to chew on. We know exactly what a parabola is, and we definitely know what a straight line is. But how might a sweeping, U-shaped parabola interact with a straight line when they're thrown together into a complex system? Do they cross once, maybe twice, not at all? Figuring out that interaction is your gateway to the next exciting level of algebra. Thank you so much for joining me on this explainer, and keep questioning the math around you.